Good morning, everyone. So today we are going to talk about deepfake. That's currently trending. 40 billion US dollar lost in deepfake tech through phishing, vishing, and voice cloning. Now, year-over-year projection says 36% growth for deepfake-related attacks. If we see the trend, it keeps on rising. There has been absolute consistency in the model that has been currently generating. It seems to keep advancing at a very higher level than we predict. But yes, there are defenses in place that we can, with correct step, we can do it. Deepfakes aren't just visual tricks right now. They are part of an end-to-end crime operations. We'll see more, we'll explain. Welcome everyone, my name is Niladri Sekhar Hore, and I am from Stonex. I work in the threat detection and automation team. A little bit about me. Okay, I'm a security researcher in threat detection and AI. We build models, we scale them, and also are part of threat detection across cloud and hybrid environments. Here is a little bit of a glossary of the talk that we are going to go through. First, we are going to touch base on deepfake evolution, and then the supply chain attack, how OSINT to monetization takes place, the blueprint for defenses that we can actively have, and then few audio samples that attackers can use and we can defend against it. And secondly, photo-based attack or image-based attack that we can prevent against. And same goes for training the model data set. Like as I said before, it has been advancing at a very high rate. So we need to train our models so that we can prevent against it, because anything that we do not see, we cannot prevent against. And also an end-to-end authenticity framework and how it can be leveraged into our SIAM tool and analyst playback tool for successful SOC operations. We are going to see that. Let's dive into it. Let's start with the context. How did we get here? Just 5 years ago, deepfake were entertainment gimmicks, but now in the evolution of generative models, from early GANs to today's diffusion architecture, has transformed deepfake into operational tools for attackers. Now, according to Deloitte, AI-enabled frauds is projected to climb from $12.3 billion in 2023 to up to $40 billion, and it's growing at a very mass rate. On your right-hand side of the screen, if you can see the projection rate, deepfake attacks has been growing, and it's growing at a very enormous rate. So here, with the high context, the takeaway is very simple. Deepfakes are no longer a niche threat. They are part of the global fraud ecosystem. Identity theft, misconfiguration, and social engineering are now supercharged by this AI, and we need to defend against it. Because diffusion models are removed from the technical barrier. They democratize creation. Anyone with mid-tier GPUs, with high availability of open source softwares, it's very easy to create deepfake images these days. So we are going to see more. Here, we talk about the deepfake supply chain. So every mature cyber threat eventually develops a deepfake model. So it starts phase-wise. Okay, the first phase being data acquisition, where attacker harvests voice, video, images, and then it goes into model training and fine-tuning. So the attacker 100% understands what the baselining is. It understands the victim's information through OSINT collection. When we talk about OSINT collection, it can be anything that you shared on open network. It can be a Facebook image. It can be a Facebook text. It can be notes scribbled on Notepad. Anything it can be. It's very powerful that the attackers use this technique to understand more about you, deceive you, and then try to exploit you either for monetary or other soulful purposes. So stage 3 would be payload construction. So when the attackers eventually get all the information about you, they start their payload construction. They do their model building. So once this model building is done, they try to deceive you. That's the next third level of tactics before they are fully exploiting you. So when we say they are deceiving you, they are using the information that has been gathered through that intel and then they are throwing it back to you either in the form of voice, video, text. The delivery method can be anything, but again, at the end of the day, it's again a AI generated based attack. So yeah, and the fourth and the last stage would be distribution and monetization with these assets that are deployed in fraud, phishing, and influence operation. Think of it as a ransomware affiliate model, creator, brokers, and operators. By understanding this chain, we can disrupt it at multiple points from OSINT monitoring to provenance validation. The OSINT phase, once it's in your biometric data, it's public. You cannot revoke. Anything that you share publicly, the intel gathered by the attackers, it's gone. You cannot revoke that. Gone. So in very light terms or in very similar terms, the moment anything is gone, so you must have seen cases where when there are weak password, it is revised that you change your passwords. Okay, but in this case, when your identity, like information, like PHI data, like personal health information data, or any type of data that belongs to you, that tags you as an identity, once it's gone, it's gone. There is no revoking back to it. As we talked about, this is the OSINT collection technique. Okay, threat intelligence and OSINT monitoring. This is OSINT to monetization. This is the synthetic media kill chain attack on how we can prevent it. Next, on point 3, we have media authentication and C2PA watermarking. So when we say C2PA watermarking, it's like verifying the source, making sure it's authentic, legitimate, and we are only trusting that. Okay, so the trust has to be ensured. Last step is incident response and attribution analytics. Whenever there is an attack, there should be an incident response team who can take care of it. Absolutely, definitely metadata plays its part. We have to know how the attack came. So the more we know about the attack, the more it's beneficial. So the incident response team takes care of it. And then we can gather more intel on it and fine tune it more as AI is maturing into it. So when we say deepfake as a service, okay, so this represents the industrialization of synthetic media creation. What started as an individual experimentation has matured into a scalable black market economy. Voice, video, full impression packages, let's numbers talk about a cloned video. Sample sells for around $300 to $800 today in the market. $2,000 for a complete business email. $1,500 for a campaign. Payment methods can be cryptocurrency, where there are high regulations of privacy. You cannot decode where the currency or the money came from. From a defender's standpoint, this commoditization lowers the skill threshold dramatically. It no longer, it's about like what we can do. It's about our detection pipeline and policies must therefore scale at the same speed at this underground economy. Telegram, Discord, dark web, marketplace host offers numerous APIs that attackers can use. These are all open sources. These attackers use to harvest data, use cloning tools. Cloning tools are right now being offered as a cloud pricing tier. They have silver, premium, platinum packages that they're on offer. With just a blink of a fingertip, you can create deepfake images of anyone. Any image that you can pick from the web, you can just create just like that. Why detection fails? Deepfake detection accuracy drops to 60% on unseen data. That's why model training is very important against the new generation of threats. Voice detectors miss emotional tone shifts because today's images are deepfakes are very, very highly classified. When I say classified, I mean it's highly tech-oriented. It's very hard to detect. If you see recent deepfake images or deepfake videos, absolutely it's undeniable to the fact that you cannot recognize it. And human fails to detect these deepfake images. There has been numerous cases on a company-wide level. People do get calls from service desk and other pillars of the company asking them they lost their system, they lost their password, asking if they can revoke their password or if they can share the password with them. These are again some of the very legitimate attack types, but yes, very, very powerful ones. Okay, so normally this type of attacks are used to deceive you, convince you to make you understand that you can share the data or the intel with them. But yep, we do have like provenance checkpoint in place. They cannot just like call our service desk and like get the password, because we do a couple of checks before we give out the information to them. So when we talk about the synthetic media marketplace, this is an underground media marketplace. Some operate publicly under the guise of AI creativity tools, where others are like fully criminal. So services, like a few of the services that are listed on the web, like is 11 Labs, HeyGen, they have legitimate use cases. Okay, but hackers do use it for their unintentional purposes. The barrier between innovation and exploitation is very razor thin. In our internal monitoring, we have seen even organized crime group offers subscription tiers, silver, gold, and platinum. These are mostly quite speculated, and the attackers brag about it on Telegram channels, saying that, hey, I successfully breached your network. I was able to do a decisive technique, and I gained access to your data. But most of them are basically hoax. But again, from a defensive standpoint, we have to make sure that whatever we are seeing, the evidence has to be backed by data. So when they say that they have breached, we have to make sure that no, the breach did not occur. So that response time, the margin to response should be very, very less. We cannot allow, so for example, if someone is saying that they breached our system, we have to come up with a standpoint with an evidence that the system was not breached. That's why we have system in place, provenance and governance. This is the small blueprint for defense, how we can prevent against it. Detection and verification resembler, synthesize ID, deepware C2PA, when we talk about source authentication in place. So defending against synthetic media requires multiple overlapping layers, not just between algorithms. So this blueprint illustrates how we merge detection, verification, identity assurance, and governance into a single detection and defensive framework. At a technical level, this AI-based detectors identify inconsistency, frequency distortion, unnatural motion, or missing psychological signals. At a identity layer, behavioral and biometric liveness, this checks confirms human authenticity. That's mostly like banks use for their know your customer purposes. Okay, and definitely fourth point, governance. There are a couple of AI regulations in place also, AI Act, NIST AI RMFC, and ISAC collaborations. This talks about how we can be more defensive on that. Next is a blueprint for defense. So when we say blueprint for defense, if you see here on the tactics and the stages used, it maps accordingly to the Mitre attack. So when we say defending against synthetic media, it requires multiple overlapping layers. At technical level, AI-based detector do identify inconsistency, but again, the Mitre attack helps us in understanding what should be the stage but tactics the attacker is using, and the Mitre technique that's exactly mapping to it, and that helps us identify what type of decisiveness like was applied to and how we can prevent against it. We are gonna go through the next step. So now, question, can we prevent this AI-based synthetic attacks? What if it's a voice clone attack? Let's see how we can prevent this. Audio deepfake detection pipeline. So this is like how we detect and classify voice samples. On the middle of my screen, you see two scenarios that says attack and defend. Okay. Due to security constraints, I couldn't share you the voice samples because again, security risks. Okay. So, but yeah, on the left-hand side of the pillar, I'll tell you how the detection pipeline actually works. So the left-hand side of the screen, the audio enters the pre-processing stage where we normalize the amplitude, remove silence, and extract key features from the voice, like LFC2, constant Q, and septal coefficients. Next, on the detection model assembles LCCN, RawNet2, and few of the other models that we used for voice feature extraction. Now, each model contributes a probability score, authenticity at the last. So we are combining the score of multi-model analysis. We are doing an assemble view, and then we are doing our authenticity verdict. So it's not one model that says this is a deepfake voice, it's not one model that says this is a real voice, but a multi-model view and an assemble average with a threshold score that's averaged out and say, okay, this is authentic and valid. Okay, this is like what we can use for the future. So on the middle side of the screen, when we say the attack scenario, the voice sample that was delivered was through a deepfake voice. Okay, that was again my voice that was delivered through the laptop's microphone, and the second voice that was delivered was an actual live voice delivered from my laptop system. So yes, so if you can see, the model predicted the accuracy here. The first one shows the voice score as false, so that's a probability scoring that's happening at the back end. And then second one shows a voice score as real, again a probability scoring. So there's a fine layer of threshold. So anything that touches that threshold, the detection takes place. Now again, how we do on the detection on the fake mark audio, extreme down below, left hand side. Flat energy in the spectrogram. These are what happens in the deepfake voice. Okay, V-coder sawtooth pattern and repeated phase bands. Okay, and on a real audio mark, we get irregular microfunctions, natural breath, and onset noise, and speech dynamics. So we have a natural breath that the model detects, and it proves its consistency over there. So this is how it works. And on the middle of the screen, you see the deep technical logic, how the model detects a cloned voice. As I said, we are using voice extraction features, and then you are using like deep natural detectors, and then some spoof probability to enable average scoring, and then we predict the verdict. Is it authentic or is it a cloned one? So now we are going to see, we talked about voice. What about images? What if the video or the image-based synthetic attacks? Let's see how we can overcome this. So I'm going to use a few of the models, okay? FNet, exception, and vision transformers. Each model works in its own phase, okay? Some works through pixels, some looks through the background inconsistencies, some looks through the head and the movement of the facial expression, and some takes care of the entire field. So we'll go into step by step on how each model is predicting. So we're going to see more on that. That's an actual hybrid deepfake detection pipeline and a model comparison. So this image is a real image of mine. Okay, we are using this model to understand what's the score it's giving for the probability on an absolute real image. So when we say it's an absolute real image, these three models come into picture. So when we talk about the first model, heuristic, that's a manually tuned model. So we are manually defining the threshold score there, and everything that's derived there, that's manually. Rest of the models are trained AI models. So we train the model to see what's real and what's not real. So it gives a probability score at the face level. It shows what the model is predicting. As I said before, each model consistencies, each model's replication is kind of different. So it's not that it's not accurate. It's accurate, but the prediction level is different. Each model behaves in a different way. So at the last, we see an assemble view. This assemble view helps us to understand how likely, with the confidence I'm saying that this is 100% accurate. This assemble view helps us understand that. So it correlates all the model's data. We have a fine-tuning threshold, and then 0.54, anything beyond that, it's likely a real image. So it's those saying it's a borderline real, but the image is real. But we can add more layers of security to it. So yeah. Next, same deepfake detection pipeline, architecture and model comparison. Okay. So when we talk about this image undergoes pre-processing, face alignment normalization, and patch extraction. Now, this image that you are seeing, that's delivered through, that's like generated through a deepfake. That's open source, available over the internet. So that's again my image delivered through a deepfake one. Okay, now we are going to see how the model predicts. Okay, so if you see, this is the same consistency that we are using. This image was put through the model test. So the model did understand that, okay, it's trying to extract the features. Each model outputs a confidence score and perceives it into a frame. So it's a frame by frame speculation. It's not that it's directly adapting the picture. So it speculates frame by frame, pixel by pixel in understanding that data or the image. It's I would say it's a pixel level classifier. So the assemble averaged the score of 0.54, categorized the image as likely real, borderline. The interpretive range is critical. Detection isn't a binary yes or no, it's a probability distribution. We can also visualize these results through GradCam overlays, allowing analysts to verify whether each model focused. If assemble converges, but GradCam shows alignment with genuine facial features, we can trust the model's neutrality. So that's the reason we are using cross-model verification, because we wanted to see how authentic and trusted the image can be. Next, now we saw each model predicts a different score, and now we are going to see how the cross-model agreement map occurs. Okay, so we are running the model again through now this is through an occlusion cam overlay. We're using a systematic blur patches of the image and observe how each model fake score changes. The hotter the color, if you see on the face, the hotter the color, the more the region influences the model's fake prediction. For example, FNet tends to focus on the first skin textures and micro noise patterns. Exception emphasizes boundaries around eyes and lips. So each model targets a different set of areas on the facial expression. WIT examines border context like facial propagation and lightning consistency by comparing these attention scores. And we can identify when a model disagrees, an indicator that the image may contain. Unseen generation methods, definitely. From a defender's perspective, this disagreement maps are invaluable. For model auditing, they show whether the assemble's consciousness stems from genuine feature analysis or artifact overfitting. In operational SOC overflows, this becomes a part of model Q&A dashboard. Every false positive or false negative can be traced back to an attention inconsistency visibility here. So that's how we are doing a disagreement between the model. Okay, for example, if we talk about the key points, occlusion cam is attention variance and analysis tool. Disagreement zones reveal model blind spots. Now we are going to talk about visualizing AI attention with the GradCam. Again, we used the FNet model. The visual represents the deepfakes model interpretability, shows how the neural network-based model can focus on facial regions during the threat or anomaly detection. At this stage, we not only classify, but we understand the facial expression, or we understand the data where it's actually coming from, or how the model is generating that this image is fake. So what it made it detect, or it gave the score. So red part of the image inconsistency, we see a red, that's an high attention zone for the model. The yellow is a moderate attention zone for the model, and the blue is definitely a low attention zone for the model. So at the back, as I said before, like models are evolving, threats are evolving. So the transparency moves us from black box AI to accountable AI in security, and model training should also be a part of the SOC analyst playbook, definitely. So that helps us scale up. Now, next, we are going to talk about the assemble performance, authentic image versus deepfake comparison. So left first column, we are using the model heuristic FNet, and these are the model classifiers. We are using an WIT exception. Okay. Now we are averaging it out. Okay, just wanted to show like how we are averaging it out, okay, and what's the beneficial towards it. Okay, so on the interpretation side, heuristic model layer sees like stays on the neutral in both, okay, and cannot separate clean fakes from natural photos. Okay, so each model comes with its own inconsistency, but each model behaves in a different way. Some are very good, okay, some needs to be retrained. That helps. Okay. From authentic image, the assemblers average scores clusters accurately. Okay, we see the real image and the deepfake image in between with both classifier examples with a probability score. Down below, we use a grading chart where it shows the grading for like fake, suspicious, and real. So the lower the score, the lower the fake metric, and the higher the score, the higher it's real. So that's how we use to gauge. But again, this can be fine-tuned according to the specific and the needs. But this is just for show purposes. But that's the scoring I'm using right now. So when we talk about a model is only good as its data. This slide shows the adaptive dataset strategies designed for constant evaluation. So we used deepfake models, deepfake images, AI images to retrain the model. Okay, we curated a balance of mix of real synthetic samples and modalities. GAN-based diffusion-based lip syncs and voice clone outputs. Each training round introduced the latest generation of deepfake engines, okay, like Style GAN 2, okay, and beyond. Adversarial enrichment ensures our models are overly fit to past artifact by including compression, noise, model augmentation, and we replicate real social media conditions where most fake circulates. So the data is gathered from a large number of places to understand, to train the model, because this has been, like deepfakes has been generating over social media, Facebook, it can be anywhere. So we are increasing our blast radius to understand and gather the data from various sources of intel. So a few key points I would like to address. Continuous advisory retraining cycle is absolute need. Multi-engine corpus, GAN, diffusion, lip sync, and voice, again. Augmentation simulate operational noise. So the goal is to generalize to unseen synthesis type. We use a combination of provenance, aware generation locks, and cross-validation with known generator fingerprints. This ensures that we are using a high confidence level labeling without a manual bias, no manual intervention needed. Now, what if the image, it's a live deepfake video to bypass system and human validation? So banks, most banks do use it for their liveness checks, know your customer type of concept. But yes, what if someone uses a deepfake to bypass that system or a human validation? Let's see how we can prevent this. Here is a small example. Again, we are using the FNet, the WIT models that we are using. We can see this can be used by any banks. This can be used by any organization that wants to perform a liveness check. Down below, we are seeing all the model probability score. Okay, so this model, this live model, kind of detects in a different way. It takes care of the facial expression, like the voice. Okay, like the eye aspect ratio, the mouth opening ratio, yaw angle for head orientation. These are computed from the media pipe face landmarks in real time. So when we combine this metrics from an like instantaneous authentication signature, for instance, here is less than 0.21, okay, and indicates a blink or deviation beyond plus 15 verified 3D presence. So it has a data backed below that talks about what should be the actual correct rate for that, okay, and based on that we are doing our synthesis to understand how the person is behaving. More to this, we can absolutely perform various other facial checks. We can say like do like very simple ones, not that complex. Say turn left, turn right. Okay, the model will understand. Okay, so the moment the subject deviates from its place, the scoring pattern changes. If the subject moves, the scoring pattern changes. If the subject looks up, the scoring pattern changes. So that's, the latency is less than 3 seconds. So it's an absolute consistent. So we can definitely perform live checks with it. Now, when we talked about real-time liveness detection, adds a physical layer of defense. Deepfakes can reproduce face, but struggles with consistent micro movements and 3D motion physics. Our system measures 3 biometric cues: eye aspect ratio for blinking, mouth open ratio more for speech and expression, and yaw angle for head orientation. These are computed from real-time media pipes, face landmarks. So when combined, these matrices from an instantaneous authentic signature, for instance, year less than 0.21 indicates a blink yaw deviation, as I said before. So this data fed into the same pipeline that we are using by our AI detectors, giving the SOC and unified authentic dashboard. Operators can now not only see the model scores, but also human motion metrics. That's absolutely important. They are real-time seeing what the model is actually doing. They are seeing what's the mortality score for that particular model. They're absolutely seeing what it should look like. So this is very beneficial for the Security Operations Center team that sits at the end of the day doing a 24/7 job. Now, we heard a lot about this image might has been tampered with. Okay, how do we prove that this image hasn't been tampered? So how do we know this image has been tampered? So how do we take care of C2P authentication? How do we make sure the source that the image or the content is coming from is 100% generic? Let's see how we can prevent this. What we can do, same image, my image. Okay, cryptographic watermarking, that's what we call as like authenticity at source, okay? So we use ED25519 digital signature that are invisibly embedded into images metadata at the time of capture or generation. Right now, I'm on the first screen, right-hand side down below, the first image I'm showcasing, that's the signature that we are using. That's only for demo purposes, displaying like how the signature looks like, okay? So this binds to the pixel data to the private key. Any exchange, cropping, recomposition, touching, or even if you resave the file, it will not match the signature. Okay, so even if the visual watermark is removed, okay, the invisible cryptographic one persistence. This approach is aligned with the C2PA and Adobe C Content Authenticity Initiative (CIA). This idea is very simple and legitimate, okay? So it carries the source, the trust at the source level till it reaches the destination level. If the same philosophy as code signing or SSL for content that we use for public and private key exchange, we use SSL for HTTPS, then why not at the image level? So verification and ingestion rather than post-incident response. This also acts as a future proof of our pipeline as a deepfake becomes harder and harder and visually impossible to detect. So this proves as a perfect model for us. Let's see how more on this. So here is a small example. So we are gonna use again models to detect. First, there are gonna be few couple of checks. We are gonna use the model to understand if the data has been or the image has been tampered with. So the first level of check that will occur is the model will see if it's a deepfake image or not, okay? And on the second level, it will see if it's actually a signed image or not. So the signing can be done at the source level. So on the source level itself, so we are using this image to sign this model first, or sign this image first. Let's do a sign. So when we upload this image, so that's called as verify at source or authenticity at source. So we are using this image to sign it. So let's first sign this image, and it will show a light visible watermark, and then the signature. So the authenticity layer will be based on signature and multi-model analysis. Let's see how we are signing this image. So we signed this image and we uploaded this image. It shows that the watermark signature is 100% valid. And if you see here on the right-hand side of the screen, you can see there are a couple of public and private keys generated. So these are used for decompiling when the image reaches its destination. So it carries the metadata with it, and it's these keys are definitely used for symmetric and asymmetric encryption that we can use when the image reaches its destination. So these are embedded within the image metadata itself. No need to separately sign the image or carry forward with the data. So the data authenticity, metadata, signing, and everything is done at the image level. It's concealed within the image itself. So the moment we fine-tune the image or draw anything recompress, retouch, or do anything, if you see the watermark signature has failed. eventually. It shows that the model is saying it's not a deep fake, but it's missing the authenticity content and it's an unverified origin, but it's though not an deep fake content. So, so this is again the end-to-end authenticity verification pipeline. So we are using an input metadata, then we are doing an cryptographic signing, followed by metadata embedding. So everything is concealed within the image itself. It doesn't goes anywhere. Okay. So we are using a multi-model analysis, then authenticity-driven verdict. The verdict comes with a multi-model analysis scoring, plus with that, we are using the cryptographic key for authenticity verification purposes. And with that verification, we are using an SML aggregation to understand for the deepfake model if it's an actual image or the image has been tampered with or anything that happens with the image. So we are using not only one level of trust, but multiple level of trust at source to reach that authenticity verdict. Now, end-to-end authenticity framework, when the system catches a fake, here we illustrate what happens when the system detects a fake. Detection isn't at the end, it's at the beginning of the response flow process. When the SML flags suspicious media, a structured alert is generated. This includes the source media ID, cryptographic hash, model scores, and confidence threshold. It's then exported as a JSON to the SOC. Analysts review the alert and verify whether the detection was correct. So their feedback is looped back into the training pipeline, improving future accuracy. This creates an adaptive feedback cycle where every detection makes the next one very smarter. The philosophy is continuous learning. The SOC doesn't just consume alerts, it teaches the model what really looks like. So here, a couple of key point takeaways: detection, verification, human validation, and retraining should be a continuous process. Structured JSON alerts for automating pipelines. Feedback loop creates self-improving detection, and human-in-the-loop assures increased trust. Yes, this is why every alerts include explainability overlays and provenance data. So analysts just can't understand why it was flagged, not just what they see. So this is a example on how we can integrate. The slide connects our framework to enterprise security operations, specifically CM and source systems, where operationalizing authenticity. Each verified alert is ingested into CM platform. It can be anything like Splunk, Sentinel, QRadar. The alert includes structured fields, media hash, signature validity, SML confidence, and severity. Analysts see it as any other security event. Once inside the CM, we can automate a triage. High severity alerts trigger SOAR playbooks, notifying threat intel teams, initiating user verification, and isolating suspicious media before it spreads into the system of the networks. So here, we can see here like post-integration results were remarkable. So when this was actually deployed, we see average analyst triage time drop by 47%, and detection to response latency stays under 3 seconds end to end. This is where detection meets operations, a closed feedback loop, combining AI and human reasoning. Key points. We can see a couple of key points here. SOC-ready integration via JSON feed, automatic triage and remediation through SOAR, measurable performance gains, 47% faster triage and 3% less than response time, and converts authenticity verification into actionable security telemetry. We have built a strong defense, but attackers are evolving too with our defense, with our advances. The threats keep coalescing. So we are going to see that. So mapping adversarial tactics into multi-layered countermeasures. So left-hand side of the screen, we can see what type of attacks based on what type of layers. It can be technical type, it can be human and tech, it can be provenance and fidelity. So evasion technique also we can see. This is a small diagram that helps us understand what can be the evasion technique, what can be the impact in detection, and what can be the defensive countermeasures, as well as the attack vector. Attack vectors consist of all the deepfake type of attacks, okay, and also data poisoning also as well, and social engineering type of attacks. So everything is covered in that map. So the road beyond 2025, we have reached almost the last stage of the slide. We have built a robust detection system, provenance, and response system. Yet advisory continues to evolve. Even new defenses creates its own set of evasion techniques. So the single line encapsulates that relative AI security landscape. For every detector, there's a counter detector. Attackers use the same generative model to stress test our defenses. The game has become iterative and adaptive. That's why continuous retraining. Remember, in cybersecurity, perfection is a myth. Persistence is the metric that matters. If asked, for example, like detection alone can't only when combined with authenticity and provenance. Verification, we can redefine what truth means in digital media. So here are a few of the key takeaways. Simulate, detect, defend, and understand. How the deepfake supply chain maps how data is stolen, models are trained and payloads are delivered. Simulate attack internals, red team your organization to video and voice cloning, detect with AI and forensics, use assemble, cross-model validation and provenance verification to spot synthetic media. Finally, defend by combining technology, policy and awareness to build a culture of authenticity. The deepfake problem is not just a machine issuing, it's a trust issue. In the world of synthetic reality, trust has to be engineered, not just assumed. So, final closing notes. We have spent decades teaching systems to trust humans. Now we must teach humans not to trust systems. Thank you, everyone.